Welcome, guys. Today we're going to review rectangular and the polar coordinate systems, and we're going to analyze and graph polar equations of conics as we develop the idea. You did a great job working your way conceptually through rotation of axes, and as always, the challenge in trigonometry, it definitely does begin conceptually, and we're going to develop some ideas as opposed to plug and chug away like we perhaps used to do way back in the day. If you do have an assignment, please look on Google Classroom. It says 4-/8 video notes. It's just an opportunity for you to really take a look at this video and tell me if you got a couple of major ideas from there that's going to help you in the problems we attempt to solve in the future. So here we go. Number one, you spent the majority of your mathematical career in what is known as a rectangular system where every point P was defined in terms of X and Y. And I remind you, a point is located somewhere. So we took the system, there it is, defined by the horizontal and vertical axis, and we were able to locate point P in a rectangular fashion. Obviously, I moved horizontally to vertically, which does comprise what, of course, is a rectangle, which is why it's called a rectangular system. And then you learned earlier this year, there's alternative systems that exist out there that help us handle different sort of curves. And one curve was a cardioid, and you might remember a couple others. I know it was a new idea for you guys, but it's called the polar system. And what do I know about this polar system? Well, instead of there being a horizontal and a vertical axis, there is a polar axis and then a point called the pole. And any particular point P, its location could be defined in terms of a particular direction of rotation. Remember, positive angles in rotational direction, negative angles in rotational directions. And then I could move a particular distance from the pole, which I'm going to call R. So any point P can be defined in terms of X and Y in the rectangular system, but also can be defined in terms of R and theta in the polar system. It's going to be very helpful for many of you to think about these systems at the exact same time. And actually, I'm going to put the polar system in front here. Well, no, I guess I can't, but that's all right. So notice, I can think about point P in both the polar system and the rectangular system. And in my mind, I can translate back and forth from one system to the other. And how do we go about doing that? Well, that was once again the joys and the opportunities that trigonometry gives to you. If I'm given any point P in terms of R and theta, and I'm trying to somehow, some way get to terms of X and Y, I think of the relationship between X, R, and theta, and Y, R, and theta. And that led me to just simply, I'll just do the cosine, or I'll do the sine. Well, since cosine of theta is X over R, it does seem prudent that I could now go from R and theta to X and from R and theta to Y. And that was very easy. At the same time, if I have been given something in terms of X and Y, how exactly do I get from R and theta? Well, when I think about X and Y and R, I always think about X squared plus Y squared equals R squared. Notice in this case that R could be positive or negative, and for us, R implies a direction. If R was positive, we would move outward from the pole. If R was negative, we would move in the opposite direction. And lastly, which trig function comes to mind with X and Y? Well, that was definitely tangent, because the tangent of theta is equal to Y over X. So I could use the inverse tangent, thinking about which quadrants it was defined in, and I was able to relate it all to locate a particular point P. Great job with that when we work through those chapters. So the conics. Notice that we developed all of these formulas, and I know we did the proof for the ellipse, when it comes to rectangular form. So if I wanted to be able to translate all this to rectangular form, or excuse me, to polar form, then I would use the tangent of theta is Y over X, and X squared plus Y squared equals R squared. And I guess I would like multiply everything out, rearrange like terms, but I know at some point that I would probably get lost. So, is there a better way? Well, people, I'd be the first to, before I even embarked on this particular journey, think, is there a different way of approaching this? And of course, there absolutely is. And it starts with us setting some conditions. So first of all, we are going to find a fixed line, and I'm going to call it a directrix. You should understand that. It is a line that helps define a conic. There's not necessarily anything else to do with the conic. I'm also going to fix a point, and I'm going to call that point a focus. And that focus will never be on the directrix. And I'm always going to place my focus at the pole. In a parabola, that's nice and easy because there is just one of them. However, there are two foci for the ellipse and the hyperbola, and you'll see how we'll address that. And lastly, we're going to recognize there exists something called E. E is called the eccentricity. And every conic has a particular positive number that relates to its particular eccentricity. And what is this eccentricity? Well, a conic, by definition, in the polar system is the set of points P in the plane such that the ratio of the distance from F to P to the distance from D to P equals E. This is long and verbose. It is why I enjoy mathematics much more than I ever did English teachers, which will take a very simple idea and make you write a 10-page paper about it. Boo. So here we go. Let's look at this. Number one, the word ratio. Even my kids in junior high should be pros at ratio. They understand it is a comparison of values using division. Second of all, I'm talking about a distance. Distance will always be defined in positive terms. And I'm talking about a distance defined in positive terms. And if a ratio involves division, then of course two positive numbers divided by themselves will be positive, which is why up here it says E is always a fixed positive number. So how about I just translate it to the language that you and I, and the notation that you and I like to use. Here we go. Ready? Eccentricity is the ratio between the distance from a focus to a point on the conic compared to the distance from the directrix to that exact same point on the conic. This is just notation. Be very flexible about your mathematical notation and make sure you can always interpret it in context of the situation. Let's investigate each one of the conics a little more closely at this point. First of all, the parabola. First thing you need to know, and you could probably intuitively figure this out, I'm just not going to spend the time to do it, is that if the eccentricity is 1, the conic is always a parabola. Make sure you remember that. It will be very helpful for you to see. The eccentricity is 1, the conic is a parabola. Here's my definition of conic. So let's look at an actual parabola that I just grabbed from a graphing calculator program. And understand that since I'm in the polar system, and now I know some of you are looking at it like this and say, Mr. Wynn, you're not on the polar system. Well, yes, I am. See, there's my pole, and there is my particular polar axis. The graphs are a little off. I kind of superimpose a rectangular system on there for you, just for the purpose of me using that graphing program. And here's my fixed line called the directrix. Notice the relationship between the directrix and this particular polar axis at this moment. Interesting. Okay, so what do I know? Well, number one, according to my definition, these must be the same. So let me identify a focus, of which for a parabola, there is only one focus. It is going to be located always at the pole. See the pole right there? That is my focus. I'm just going to always place a focus at the pole. It'll make my life very easier. By definition, the distance from the focus to the point, and you know what? I think I'm going to grab this point. Let's see if I grab. There we go. I'm going to grab this point right. That's not what I want. This one right here. I'm going to grab the point on the parabola. It seems easiest for me to understand, and it's the point called the vertex. Make sure you understand that. In fact, I'm going to clean this answer up a little for you guys, just to get rid of that R and theta, because we're not going to worry about measurements and things on that yet. There we go. 10 seconds. Vertex. Very nicely done. What does my definition say? It says the distance from the focus to that point, which in this case is that vertex. I'm going to show you guys right now by grabbing this line. There's the distance from this point to that point. A little cluttered in here. Must be the exact same as the distance from the directrix to that point. Let me grab that right over there. So all it's trying to tell you is that these two distances, these two pink segments are the same. Now, is that true for every single point P? Well, yeah, it needs to be true for every single point P. So let me just grab another point on this parabola. I apologize, this is not drawn perfectly to scale. I'm going to do my best here. And I'm going to grab, let's see if I can grab that. There we go. Nicely did. I'm going to grab that right there and that right there. Now, the distance from any point of the parabola to the directrix, always remember, it will be, in this case, measured along the straightest line, horizontal. I'm going to compare it to the distance from that point to the focus. And the idea is that, it may not look exactly right here, but that's the idea, is that this distance and that distance are the same. In theory, it creates an isosceles triangle. And it doesn't matter where that point goes, or that I grabbed it and I put it way down over here. All that matters is that distance and compared to that distance is the same. And once again, I know that doesn't look perfectly. Give me some grace as I work my way through this. So that's the definition. So I have my focus will always be at the pole. In this case, notice the vertex is exactly in between the focus and the directrix when the directrix itself happens to be a vertical line. Also notice that my parabola opens up horizontally. I bet if the directrix was a horizontal line, things would change. I bet if the directrix was over on the other side, things would change. And that is something we will reason out, and then we will figure it out. So let's move on. How about the ellipse? Two important things to know for the ellipse. First of all, if the eccentricity value happens to be less than 1, then the conic will always be an ellipse. Good to know. Now, how could the eccentricity be less than 1? Well, it has to mean that this distance from the focus to the point on the ellipse must be less than the distance from the directrix to a point on the ellipse. What is also nice to know, we're not going to take the time to prove, is that for an ellipse, the major axis is always going to go through the focus, and it always will be perpendicular to the directrix. So notice that I have a vertical running directrix, and I have a horizontal ellipse. Interesting. By definition, I always start with one focus, and I'm always going to place it at the pole. And at this point in time, it looks like I've cleaned up the rectangular system a little for you guys here, and the pole and the origin are one and the same. There's my pole. There's my polar axis. My first focus, based on the definition, will always be at that pole. So what else does it tell me? It tells me, supposedly, that, let me move this out of here for 1 second, that any point on the ellipse, like let's say, I don't know, this point, or maybe that point, but that point just happens to be a vertex. So I'm going to actually grab that, put it there, and you know what? This was also a vertex. It doesn't matter where the point on the ellipse is. What matters the most is that, by definition, the distance from the focus to this point compared to the distance from the point to the directrix, for it to be less than 1, this distance must be less than that distance, and you can clearly see it is. And it doesn't matter where the point goes. Sure, the distances change, but the relationship between the distances do not change, which is that the distance is always shorter to the focus than it is to the directrix. it will always be less than 1. It's going to define an ellipse for me. So let me maybe clean a little of this out here for you guys and point out number 1, that this right here and that point right there, they serve a great purpose for us because, as you can intuitively see, exactly in between the two vertices, according to our rules of A and B and C, were the endpoints of what is called the major axis. Now, if this is in the polar system, what angle am I talking about? I'm talking about 0. And what angle am I talking about? I'm talking about a pi. And this creates the major axis. What's the relationship between the major axis and the minor axis? They are always perpendicular to each other. So it only goes without saying that if the major axis is perpendicular to the directrix, the minor axis is always running parallel to the directrix. Interesting. Now, what angles do I plug in for this and this? Well, I would never plug angles in. I would recognize I could figure out the distance from the center of the vertex. I could figure out the distance from the center of the focus because I always place it right here. Now, where's the other focus? Well, it goes without saying the other focus is going to be right there. The center is the midpoint between this particular segment that connects the foci. The center is the midpoint between the segment that connects the vertices, and the center is the midpoint between the segment that connects the minor axis. Interesting, and we're going to take a much more numerical approach to the ellipse in the probably next lecture we do. So lastly, how about the hyperbola? Logic, people. Here we go. Same definition of eccentricity, but it goes without saying because it's the last one we're talking about. In this case, if it's more than 1, the conic will be a hyperbola. Well, for a fraction to be more than 1, that means the numerator must be greater than the denominator. So now we're talking about a distance from a focus to a point on the hyperbola must be greater than the distance that point is to the directrix. So how do we always start? Well, this whole point focus right here, right now, we're always going to place on the pole. There it goes, just like that. And notice that when I grab a particular point on either branch of the hyperbola, I'm going to go with this one right here, and I evaluate the distance from here to the directrix. In this case, since the directrix is running vertical, it looks like it defines a horizontally opening hyperbola. The distance from there, that point, to the focus, well, clearly in this case, the numerator is much greater than the denominator. Doesn't matter where I go. Yes, absolutely. The distances may change, but the relationship stays absolutely the same. You see it? Well, this one's a little tighter. This distance is clearly still more than that distance. You know that because we understand the concept of right triangle trigonometry. So, ladies and gentlemen, probably because I should have drawn a little better. There we go. Very nicely done. So, what else could I figure out? Well, number 1, if I know this will always be located, this is a focus, it will be located, be aware that the transverse axis is always perpendicular to the directrix is always perpendicular to the transverse axis. What is the transverse axis? Well, the transverse axis is the values are the endpoints that connect the two vertices. Notice what angle would I have maybe plugged in? Maybe 0. What angle would I have plugged in? I would have plugged in pi. You got to think about the polar coordinate system. Well, how did I end up over here? Probably had something to do with negatives going on. I'll have to figure that out when we arrive to a problem dealing with numbers. What's the relationship between this right here, which is the transverse axis? Well, I know the center of the hyperbola is always in between, and there it is. Now, if I look closely, I have the distance from the center to a vertex. I have the distance from the center to a focus. I have the distance from the vertex to a focus. So it goes without reasoning, I could numerically figure out where my other foci is. I'm just going to wing it by putting in there. And at the same time, because I now have this distance and that distance, I, of course, would be able to locate exactly where my conjugate axis is, which would be the b value. Because remember, for hyperbola, b squared is equal to c squared minus a squared. For an ellipse, b squared is equal to a squared minus c squared. Subtle nuanced differences you have to keep track of. Once again, that's why we get paid the big bucks. From there, I'd be able to draw my asymptotes if I was in the rectangular system. So, ladies and gentlemen, that was just an introduction to beginning to develop the language of the polar system with respect to conics. I know there's going to be a lot of you, just like your first year perhaps of Spanish, of you just recognizing something in Spanish translated to English. But we're going to get to the point where polar is polar and rectangular is rectangular, and you're going to be able to jump back and forth for whatever reason you deem necessary. Have a great day.